All right, you guys get to listen to me for a while again now. Sorry about that. So this is a rewritten version of a talk that I've done a few times at various events, and the point that I was trying to make didn't seem to be getting across quite right. So let me give a first attempt at this rewritten version. So the hard part of software switching, in my opinion, after writing a couple of them, is usually making it fast. It's not that hard to write a switch if you're just going for, say, correctness or flexibility, but when you add in performance, that makes it harder. So there seem to be sort of three keys to performance that I've listed here, and other people might break it down differently, but I think these are legitimate. First, you need some way to get packets to and from your network interfaces, whether they're physical or virtual, fast. So fast packet I/O is definitely key, and that is where projects like DPDK excel. The second is that whatever infrastructure you're using for your switching, that has to have low overhead, so that when you do get packets in, you don't have a lot of overhead just to start dealing with them. And finally, your per packet actual packet processing cost, that has to be low as well. So I'm going to go through these. So, but one thing I'm not going to talk about is something that I consider more or less a distraction, the mix between whether your code is implemented in the kernel or in user space or some kind of a mix. This tends to move back and forth almost like a trend or a fad. And I've even seen a project where they're working on running DPDK in the kernel. So it's not even like it's fundamental to any one of these projects. So let's talk about packet I/O methods. I've listed a whole bunch of them there. Packet I/O is important, and it is more or less independent of the switch architecture. You can use most of those, or maybe all those, with OpenVSwitch. But it's not really what I want to talk about today. There's lots of interesting things to say about it, but I don't care today. One key thing to keep in mind is that the packet I/O method is not comparable to a complete software switch. People who are pioneering new packet I/O methods like to do benchmarks on the packet I/O method itself, which makes a lot of sense. But sometimes they end up comparing them to a complete software switch, and that ignores these points 2 and 3 that also make a big difference. So I just want to point that out. So my second point of the list is that you need low per packet overhead. So here's a diagram of a common way to organize a software switch. A packet comes in, it goes through a series of stages. Maybe it branches, maybe it joins back up, and eventually the packets go back out. So commonly you implement that as a series of function calls, or maybe a series of calls through function pointers, and that has very low overhead, and it has additionally loose coupling among the stages. They can all do pretty much whatever they want. There are no real restrictions. They're just written as code. So OpenVSwitch immediately has a disadvantage here. In addition to calling through all these stages and so on, OpenVSwitch also sticks a parser at the beginning. So that increases overhead, and it sounds like a bad idea. Let's sit on that for a minute. Now let's talk about my third key here. So in your typical switch, like I said, one of your stages is just a function that you call into. So that function, it can do whatever it wants. It can maybe it does nothing and just drops a packet. Maybe it changes the packet. Maybe I don't know. It could split the packet into 2 packets. And there's basically no overhead on the function call itself. And you often see switches tested with what I refer to as a null pipeline, a pipeline that does nothing. It has no stages, or maybe just one stage. So that's what you often see in a typical switch. Now, OpenVSwitch again has a penalty here. So in OpenVSwitch, each stage is a general purpose network classifier. And so that's really expensive to implement in software. We've worked really hard to make it as cheap as possible, but it's still it's still much more expensive than your special purpose code that might want to do something. And in addition, if you do it in the most straightforward way, then you have one of these classifiers, one of these expensive classifiers for every stage. So based on that, OVS immediately has two strikes against it performance-wise. It has high per-packet overhead from its infrastructure, and it has high per-packet processing cost from all of these classifier lookups. And furthermore, it has a limited choice of what you can do because your actions are limited. And so, therefore, OVS must be slow, except that you can cache things. So I'm going to talk about caches quite a bit and just sort of lead up here with an introduction to caches and networking. Caches have kind of a mixed history in networking. They certainly are used a lot. You can think of Mac learning as a kind of a cache, and I think that most switches still do Mac learning. ARP and neighbor discovery is definitely a cache. And generally you have route caches, or at least in older versions of Linux, although famously Linux removed its route cache some time ago. And that gets back to the overall bad reputation that caches have in networking. One of the problems there is that the hit rate generally depends on the traffic, and that means that you get unpredictable performance when you start throwing caches into networks. And networking people really love to say that they can process the maximum packet rate at the shortest possible packets, and so unpredictable performance means it's hard to say that. And then cache invalidation can be tricky. So caches are used in networking, but they have a really mixed reputation. So with that in mind, think about how we would optimize OpenVSwitch to make it faster. So the simplest way to do this is to take a cache, and I'm representing those as $signs, just it's kind of funny. And there's a bit of a history in chips anyway for using a $sign for a cache. Anyway, so you can add a cache to each of these stages, and this helps, but it really isn't an advantage for OVS because you can do the same thing with any other software switch with the ones that I was talking about that are not OVS. And so if you spend the same amount of effort putting caches into each of your stages in both OVS and other switches, OVS is still going to have extra overhead and will still be slower. So that's not what we actually do. OVS does something that, at least for the purpose of this talk, I'm calling compound caching. Instead of caching each stage individually, it has a cache that covers the entire pipeline. A packet comes in, and then after it passes through all of these stages, we add something to a great big global cache that covers everything that happens to the packet. And then if a second packet that resembles that one in important ways comes in, then it bypasses the entire pipeline. So this is a trick that other switches might consider doing, but it's actually much harder than caching individual stages. And I'll talk about that a little bit at the end of the talk. But for now, let's talk about sort of some of the properties here of what I call compound caching that we have in OpenVSwitch. So the effect here is that we take all of these stages that the OVS pipeline has in some given instance, and we effectively cross-product them into a single stage. And the paper that we had at NSDI, a good portion of it was about this and how it works and how we keep it effective. And one of the things that you might immediately think is that it's too expensive to cross-product all of them because you have exponential blow-up. But we actually do it in a lazy way so that doesn't happen. So if you postulate that this works, then what you end up with is that The base cost of forwarding a packet is still fairly high because you have the parser step that we still have at the beginning, and then we have a single classifier lookup that we need to do to look into the compound cache. So that classifier lookup, it's still a significant cost, but you're only doing it once, even for a complicated pipeline. And so the result is that regardless, more or less regardless of the number of stages you have, whether it's 1 or 20 or 40, the cost for forwarding a packet is about the same as if you had only a single stage. And that means that, in effect, a null pipeline, a very short one, is relatively slow, and it's never going to compete with something that's hard-coded. It's never going to compete with a very simple program in, say, DPDK or VPP. But on the other hand, if you're trying to do something complicated that would be harder to implement quickly in a system like that, then it's relatively fast because you don't lose much performance for that number of stages. I'm not going to cover it in this talk, but hardware classification offload is also possible, and that would get rid of most of the cost of that classifier lookup. Our panel later on will talk about that a little bit. So to hammer home the point I'm trying to take a little bit more, take a look at this graph. And this isn't a real graph, I just made up the numbers. But the goal is to show you the point I'm trying to make. So you can see in the blue there that as the number of stages increases, the forwarding latency for OVS doesn't increase very much. But more typically in your sort of typical switch architecture, software switch architecture, you'd see that as you increase the number of stages, then more or less you can expect that the cost of forwarding will increase proportionally with that number of stages. Now, caches are still problematic for networking. So over the years, we've invested a lot of effort into making sure that our cache hit rate is as high as possible. And again, the NSDI paper has a lot on that. So that's my main point, that yes, OVS will be slow if you're comparing it to your switches that are doing simple things and doing them at maximum packet rates. But if you're comparing OVS doing something complicated, like network virtualization, for example, and that's one of the applications that we've more or less optimized for over the years, then I believe you'll see that the performance is better than anything else out there. So the big question in my mind is, can other switches that are built using other architectures obtain this sort of performance advantage too? And I think the answer is yes, but it'll require some work. You won't be able to just hack on the infrastructure. You'll have to actually modify the stages themselves. And what you need to do is each of those stages needs to record its read and its write dependencies, and it needs to be able to somehow record the actual actions that it's going to take, rather than just executing those actions. Probably that requires the stages themselves to actually be rewritten. Another good question is, if these sorts of benchmarks that show, say, basically using a software switch as a very expensive crossover cable, if those aren't fair to OVS, if those don't demonstrate its performance in an interesting way, what is a good benchmark? I don't have one to propose. Maybe something involving OVN, but I'm beginning to believe that that's something that we should work on and we should propose. Thank you. That's my entire point. I think we have time for some questions. Yeah, we have 5 minutes for questions if anybody wants to come up to one of the mics. All right. Oh, we have a question.
Thanks for the caching clarification. So do we have any configuration in the tutorials or somewhere where we can play around with this caching factor so that
OVS tries to optimize itself for whatever flow table is actually in use. I, I'm not sure that there's a way to really adjust that in most cases. I think the thing to do would probably be to try out more complicated and less complicated flow tables. For example, if you set up something that's just doing simple switching, and compare that to, say, an OVN configuration where you've got logical switches and a couple of logical router hops in the middle. That's where you're going to see the biggest benefit from this sort of caching.
All right, sounds good. Thank you.
Thank you, Ben. Thank you, Ben. That was.
Is everybody okay? Is everybody okay over there?
So I really love to play with this compound caching. Is that already in 2.5 or 2.6?
Well, that's been in there since 1.11, and we've been refining it over the years, so it should be really dialed in now.
Thank you.
So I've not read your NSTI paper, so since we have time, I'm going to ask you these questions. How do you match the packets? Because the parsing itself is expensive. So how do you match the packets?
So we have not done anything to optimize the parser, although P4 has a lot of potential in that area. The matching is done using a fairly straightforward kind of classifier called a tuple space search classifier, and we've just improved our implementation of that over the years so that it's as fast as we can make it. I don't know whether I answered your question.
That's what I wanted to know, because one of the overheads is that when two packets come in, you want to use the same cache, how do you get the cache rate?
Oh, I see what you're saying. The way we have a way to basically figure out what fields are actually important based on the flow table. So if the flow table does not match on the source IP, then that won't be considered during caching. And so any packet, regardless of its source IP, would be represented in the same cache entry.
Thank you.
You're welcome.
Thanks for a great talk, Ben. You mentioned that Linux colonizing with the routing cache. The main reason for that is that Linux is often run in an untrusted org environment, and the average behavior was found to be more important than the worst case. The worst case before was found to be more important than the average performance, which led us to basically reintroduce caching at different levels. So we're caching routes for sockets, which means that we need to establish the full connection first, which makes it more difficult to actually fill up your cache if you're untied. Do you see OVS could do something similar as well and protect its cache?
Boy, that's well. First of all, I think that's a great summary of the argument you often see against caches and networking, that the worst case performance is more important than the average case performance. Second, about whether OVS could protect its caches. Well, so the caching mechanism that we use now, based on what we call megaflows, is actually in some ways a response to that sort of issue. Before megaflows, fairly uncommon but still important traffic patterns like scans and so on. Even sometimes they would happen accidentally, could very easily pollute and kick things out of the cache. The megaflow cache that we have now is much more effective at protecting that. As time goes on, if we discover that it still isn't effective enough, then I'm sure that we'll move on and try to figure out something that's even better. Thanks, everyone. We now have a break that lasts for 15? What time are we back, Justin? And please be back at 10:30 in just under 20 minutes. Thanks, everyone.